So let's look at this question. It says, one end of a light spring of natural length A and modulus of elasticity, 4 mg, is attached to a fixed point or the other end of the spring is attached to a particle A of mass km, where k is a constant. Initially, the spring lies at rest on a smooth horizontal surface and has length A. A second particle B of mass m is moving towards A with speed root of 4/3 GA along the line of the spring from the opposite direction to O, as seen on the diagram. The particles A and B collide and coalesce. At a point C in the subsequent motion, the length of the spring is 3/4 A, and the speed of the combined particle is half its initial speed. So on part A, find the value of K. Okay, so looking at this question, there are two main things that we need to take account of. We need to consider first the fact that there's collision of particles going on here. And so we're going to need to consider the principle of conservation of momentum. And we're also going to consider the principle of conservation of energy as well. Okay, so those are the two main things. Let's start with the principle of conservation of momentum. From the information given, the particle A has a mass of km and particle B has a mass of m. Initially, particle A is at rest and particle B is actually moving towards A, all right, and with this particular speed. So according to the principle of conservation of momentum, the momentum before collision should be equal to the momentum after collision. Before collision, particle A has a momentum of 0 since it's initially at rest. Okay, so I'll say here 0. And then for particle B, the mass is m and the speed is √4/3 GA. It's going in an opposite direction into the left, so let's just say negative. So that's going to be minus mass times velocity, okay, 4/3 GA. This has to be equal to the momentum after collision. But what's happening after collision, okay, or at the point of collision? At the point of collision, we can see that actually we've been told that the particles A and B will collide and coalesce, which means they now have a combined mass of km and m, right? So the mass is km plus m. The speed, okay, that they have at that point, just after collision, I'll just call it v. And v will be going obviously in this direction, right, which will be negative as well. So I'll put a negative here, v. All right, so this is what we are having. We'll have that as minus m of the square root of 4/3 GA is equal to, I'll factor out m here, so it's minus m of k plus 1 of v. And we can divide both sides by minus m so that we have, because we do not know what v is, all right? Making v the subject will be the square root of 4/3 GA over k plus 1. So we will leave it at this. I'll just call this 1 as we might need it a little bit later. So at this point, let's move on to considering the conservation of energy, all right? And from the principle of conservation of energy, we're going to say the initial energy is equal to final energy. Now, initial in the sense of here, just as soon as the particles combine or coalesce, that is the initial point. And the final point, according to the question, they say at a point C, right? They say at a point C in the subsequent motion, the length of the spring is 3/4 A, and the speed of the combined particle is half its initial speed. So final is at some point C, all right, where the length of the spring will be 3/4 A, and the speed of the combined particle is half its initial speed. Its initial speed was v, so the speed will be half v. So that is the point F here. All right. So we have I and F right here. So let's start with the I, the initial energy. Initial kinetic energy will be half times the mass. Remember, the particles have coalesced, Km and m. So it's Km plus m times the speed squared, v squared. All right. And the initial elastic potential energy is 0 because at the point I, or the point A, the spring has its natural length. For the final energy, that's now the energy at F, where the speed is now half v. All right, so the kinetic energy will be half m. M is the combined mass, Km plus m, times the speed squared, that's half v squared, plus the elastic potential energy here will be, now this is a compression, okay, but still Hooke's law applies. So the modulus of elasticity is 4 mg. So I will say here 4 mg times the extension squared. In this case, it's not really an extension, it's a compression. It's going to be 1/4 A. That's the compression, okay? When the particle moves in this direction, it's 1/4 A. Okay, to make it plus 3/4 A gives us A, right? So it's A minus 3/4 A, it's 1/4 A. That's the compression. So 1/4 A squared over 2 times the natural length. Natural length is actually A, right? So A. And this is what we need to simplify. All right. So let's carry on with this. With what we have on the left side, that's half of Km plus m of v squared. And on the right side, we have simplifying this, 1/4 times half, that's an eighth of Km plus m of v squared. And that's plus, simplifying this, we should get 4 times 1/4 squared all over 2. This gives us an eighth of mg, then a squared over a is a. So this is what we will be having. I'm going to take this to the left side. So a half, okay, if we take this to the left side, a half minus an eighth is 3/8. So we have 3/8. And let me write it a little to the left. 3/8 of Km plus m of v squared is equal to an eighth of mga. Right, I'm going to multiply both sides by 8. And I'm going to have 3. I'll factor out m as well. So we have k plus 1 of v squared is equal to, here the cancel, mga. We can divide both sides by m. So, and make v squared the subject. So v squared will be equal to ga over k, actually 3 of k plus 1. So this is coming out from, I'll call this 2. All right, this is coming out from the conservation of energy. So with what we have right here, remember, equation 1 is as V equals to something, all right? And equation 2 is V squared. So we can say equation 1 squared is equal to equation 2. We can equate the two equations. Equation 1 squared gives us V squared. So if we square a root of 4 thirds GA, we get 4 thirds GA. And that's over, at the bottom, we have K plus 1. So it becomes K plus 1 squared, being equal to this V squared, which is GA over 3 of K plus 1. All right. Now we can see that the GAs do cancel out. All right. And we can multiply both sides by 3 of K plus 1. This side as well by 3 of K plus 1. If we do, we will be having, okay, here they cancel. So 1 on the right side, and on the left side, these 3's cancel. So we have 4 of K plus 1 remaining. Actually, the K plus 1 on top divides into one of the K plus 1's at the bottom. So we have 4 over K plus 1 remaining, being equal to, on the right side, 1. All right, which leads to 4 is equal to K plus 1 if we multiply both sides by K plus 1, which then gives us K to be equal to 4 minus 1. That's 3. So K here comes out as a 3. Okay, I don't know if you followed through what I did.
That's okay, sir.
All right, it's fine. So that's basically how we would work out part A to get the value of K. Now there's a part B. Let's go on to part B. It says at the point C, the horizontal surface becomes rough with coefficient of friction mu between the combined particle and the surface. The deceleration of the combined particle at C is 9 over 20 g. So in part B, find the value of mu. All right. So here they're talking about the point C. They say at the point C, the horizontal surface becomes rough. Okay. So remember, we had a horizontal surface, some fixed point around here. All right. And the spring, and we had a point A here. All right. And at some certain point C, according to the question, the surface becomes rough. And remember, the particle is still moving to the left. All right. So there's further compression. Okay. But the force, the spring force is still acting, actually will be acting outwards like this, and it's the thrust, and I'll call it T, even though the particle is moving to the left, but the thrust is directed to the right, okay, opposite the compression direction, okay. We also have friction to talk about, because since the particle is still moving to the left, it is also under friction going to the right, F, okay. So basically, if we are to resolve the forces, this is just direction, right? If we are going to resolve, that's going to be the resultant force, okay, will be the thrust plus the friction, all right, is equal to mass times acceleration. Now, mass, total, the combined mass is, remember, Km plus m. But we've gotten K to be 3. So it's 3m plus m. So basically, it's 4m. So it's 4m times the acceleration we've been given, which in this case is a deceleration, 9 over 20 g. Okay, so this is what we have. And we're also going to make use of the fact that we know that we can calculate T as lambda x over L. In this particular case, T is the thrust. So T is equal to lambda, uh, which is 4 mg, according to what they gave us. 4 mg times the extension. Remember, they told us that actually we established that it's the third A. That's the compression in this case. So it's a quarter A. All right, so we have a quarter A, all right, over L. L is the natural length A, basically. So we know that this is equal to, okay, the A's cancel, fours and fours. Well, it's just mg, all right. And we also know that, for the particle, when it is at C, there is a normal reaction and the weight, remember, is 4m, so 4 mg. So we also know that R is equal to 4 mg, which means that F is equal to mu R, therefore, okay, therefore F should be equal to mu. Okay, do they tell us what mu is? Okay, oh, that's what we're looking for. Mu times R, which is 4 mg. Okay, so mu of 4 mg basically. So if we take this equation, all right, equation I, and I place it here, T is mg, F is 4 mg of mu, has to be equal to this thing here, okay, which would be, okay, 4 goes into here 5 times. So it's 9 mg all over 5, basically. So we're going to take the mg to the right. So we have 4 mg mu being equal to 9 mg over 5 minus mg, which is 4/5 mg, right? And we divide, oh, let's multiply both sides by 5. So that's 20 mg mu is equal to 4 mg. And let's divide both sides by 20 mg over 20 mg over 20 mg. So they cancel here to give us mu s. The mg's here cancel. 4 over 20 is a fifth. So this has to be the value of mu.